Next, we will discuss how to find the limits of rational functions using the analytic approach. First, let's figure out what does a rational function look like. Rational functions are ratios of polynomial functions. When polynomials in the numerator and the denominator are both written in standard form, then such rational function is said to be in standard form. In standard form, we can easily read the leading coefficients and degrees of the polynomials in the numerator and the denominator. If the degree of the numerator is less than the degree of the denominator, then such rational function is called proper. Otherwise, it is called improper. Improper rational functions can be rewritten in quotient form by performing a long division on polynomials. In quotient form, we can identify the quotient, remainder, and divisor, which are all polynomials, and therefore have their own degrees and leading terms. When polynomials in the numerator and the denominator are both written in factored form, then such rational function is said to be in factored form. When a rational function is written in factored form, we can easily read the zeros and the multiplicities of the polynomials in the numerator and the denominator. Of course, for each polynomial, the sum of all multiplicities adds up to the degree of the polynomial. If the numerator and denominator have no common factors, then such rational function is said to be in reduced form. If there are common factors, then we would write the rational function in reduced form by removing the common factors from the numerator and denominator. If during the reduction process some factors in the denominator disappeared, then the rational function has a removable discontinuity at the corresponding point. Otherwise, there will be a vertical asymptote at all values where the denominator is 0. On the other hand, all values where the numerator is 0 will generate the x-intercepts of the graph. Moving forward, we will assume that all rational functions are in reduced form, and if not, we will try to reduce them. For a given rational function, the goal is to be able to find the following limits: the end behavior and at some finite value a. To find the end behavior limit, we would like to have our rational function written in standard form. And to find the limit at some value a, we would like to have our rational function written in factored form. So let's find the end behavior limit of a rational function written in standard form. Recall that polynomials behave like their leading terms when x approaches to infinity. Therefore, it is reasonable to suggest that a rational function that is a ratio of two polynomials will behave like a ratio of their leading terms. From this relation, we derive the following strategy for finding the limits of rational functions when x approaches to positive or negative infinity. First, we truncate each polynomial, leaving only the leading term. Then, we simplify the resulting expression to end up with a limit of a power function when n is greater than m, or a limit of a reciprocal function, which is always 0 by the way, when n is less than m, or just a number when n is equal to m. So let's find the local limit of a rational function written in factored form. Recall that continuous functions approach their own outputs. Therefore, if the target value a is not equal to any of the zeros of the denominator, then the limit of the function is simply equal to the value of the function at that point. In case when the target value is equal to one of the zeros in the denominator, the function will have a vertical asymptote, which means that the limit is equal to positive or negative infinity, meaning that we do know that the answer is infinity, we just don't know whether it is positive or negative. In this case, we pick a test value which is very close to the target on the appropriate side, and then plug it into the function in factored form. The good news is that we only have to keep track of the signs of each of the factors. So if the total multiplicity of negative factors is even, then the limit is positive infinity. Otherwise, it is negative infinity. We discussed how to find a limit of a rational function using the analytic approach.